In this mini course, we're going back to the basics. Many cybersecurity professionals don't fully understand how common protocols and networking concepts work, largely because they've never interacted with these protocols beyond the theoretical level. Think about it. Have you ever seen how DHCP or ARP packets work? Do you truly understand packet encapsulation and decapsulation? Have you seen how TCP sessions end with reset packets or witnessed an actual TCP three-way handshake? If you answered no to any of these questions, you'll find this mini course valuable. In just over an hour, you will level up your networking and protocol knowledge. My goal is to transform some of your theoretical knowledge from the CompTIA Network Plus or Security Plus into practical understanding by showing you how to interact with these protocols and demystifying the complexities of computer network. So if you're interested, let's dive in. But first, please be sure to like and subscribe, as your support helps me create free content like this. If you want to join our Discord community of almost 6,000 members or subscribe to our cybersecurity newsletter, you'll find the links in the description. Finally, check out store.cyberworks.com for some amazing cybersecurity merch. That being said, let's dive right into the course. This video is going to be a quick introduction to Wireshark. So first things first, we have to download Wireshark. So I'll be showing how to download Wireshark both on a Windows device and a Linux device. So here, this is a Windows device. So in order to download Wireshark, just go navigate to www.wireshark.org and click on download. But before you download it, I also recommend checking out the Shark Fest, which is a great conference if you're trying to learn more about Wireshark. If you cannot go for the conference, definitely check out the Shark Fest YouTube channel. It has tons of videos that are really educational in terms of learning about Wireshark, either for networking, security, whatever it is you want to learn about Wireshark. It has tons of videos, so definitely check out either the Shark Fest conference or the Shark Fest YouTube channel. It's definitely a great learning resource for Wireshark. So let's go ahead and download Wireshark. So click on download, and based off of your operating system, you can download it. So I'm using a Windows device, so I would use this Windows installer. So you click it and it gets downloaded. If you're using a Mac device, this is what you're going to be using. So I'm not going to be downloading it because I already have it downloaded, so I'm just going to be going straight to the installation process. So of course, you navigate to your downloads folder and double click on download, and then we'll click yes and click next. We're just going to go through the defaults. We're not going to change anything here. So noted, next, and I would like to add a desktop shortcut. So I'll add that. You can choose to. If you don't want to, you don't have to add it. So we're going to click next, and we'll leave this as default. Next, install. And while that installs, I'm going to show you how to install it in a Linux device. So let's switch over to my Ubuntu virtual machine, and here it's super easy to download it. So you definitely need to have root user privilege in order to download Wireshark. So we use sudo apt-get apt-get install Wireshark. And it's not going to download it because I already have Wireshark on this device. But if you did not have Wireshark, it will download it to this device. So it looks like our Windows device has a prompt for our Wireshark. So after its installation, it asks for a license agreement. So we agree to that. I'm not going to click anything here because I don't really think I need any of this. So I'm just going to click install. Just a basic and default installation of Wireshark, and this should not take too long, and it should install in a moment. While we wait for that, let's navigate back to the Linux device. And here, I just want to show you how to start Wireshark. So you can either go to the applications and click on Wireshark to start it, or you can do it. My favorite way is by starting it from the terminal. So you can start it with just type in Wireshark, and it will immediately start the Wireshark application. But here, the problem about starting it from here without root user privilege is that you're not going to be able to capture live data. So if we try that, so if we click on this particular interface, it's going to show us the capture session could not be initiated because you do not have permission to capture in that device. So in order to have permissions, we use the sudo Wireshark, and it starts Wireshark. And now if we choose to start a packet capture here, it will ultimately start capturing network data in our network. So that's quick and easy way to start Wireshark in a Linux device. So back on our Windows device, if we click next and finish, the installation will finish and we'll have Wireshark. It just takes a little bit of time, but not too long. And it's completed, so click next and finish. All right, cool. Let's close that out. And starting Wireshark in Windows is pretty easy. We can access it from our desktop like we selected. So we selected to have a shortcut on the desktop, so we can access it from there. So just double click on that, and you don't necessarily need any form of like administrator privilege in order to capture live network data. So if we choose this particular interface, as you can see, there's multiple interfaces here. But let's just choose this Wi-Fi interface and start packet capture, and we'll see we didn't have to use any form of user privilege or anything. It just starts capturing data, so that's a great thing. In order for us to stop the capture, we just click this red button right here, and it stops. If we want to start it over again, we'll click this. However, it will prompt us to if we want to save what we've already started, or if we want to continue without saving. So I don't really want to save it right now, so I'm just going to continue without saving, and it pretty much starts back a new packet capture. And that's essentially how to start and stop packet captures. So for security analysis, we want to have some specific information on our Wireshark dashboard. So right now what we have is just essentially the packet number, the time, the source, the destination, the protocol, the length, and the info. And this is pretty good information, but we don't have enough visibility for a good analysis. Essentially, what we want when we're analyzing stuff from a security perspective is we want to see the source IP, but we also want to see the source port and the destination port, amongst other things. Other things could be the host name, or maybe more HTTP data, which will probably be seen in here. But specifically, we want to add the source port and destination port. So there's two ways we can do that. The first way, let's try to add a source port. So the first way we can do that is directly from the packet header. So if we navigate over here to the user Datagram protocol header, and we right click on source port, we can apply it as a column. And as we can see here, we immediately have a source port column here to show us a source port, and we can drag that over here to have the source port right beside the source IP address. Now the second way to add a column is by right clicking on anything here. So right click, and we can choose column preferences, and here we see all of the columns, and here we can choose to add another column. So if we click add or the plus sign right here, it adds new column. So let's delete the second one that was added by mistake. So let me remove that. And here we can specify the purpose of this column. So let's say we want this column to be destination port. So we can just say DSD, or just say DSD underscore port, but let's leave it at DSD for now. And we can specify the type of information we want this particular column to cover. So here we have tons of things that this column can have. So we see like all of these different things that could be in this destination, in this as a type for this particular column, because we see destination port, destination address, frequency, channel, all of that. But what we're concerned about now is the destination port. So we can choose either destination port, either this destination port or the destination port unresolved. But I'm just going to choose this generic destination port. So click that, and we click OK, and we can see that the destination port should be added to our, all right, so it was hidden all the way over there, but we can see that the destination port is added to our packet capture, to our dashboard right here. And if we pull this back a little bit, we can drag it to after the destination IP and just makes this a little bit smaller. All right, and there we go. So we can see right here we have our destination port. I meant to put that right beside the destination. All right, so we can see we have our destination port right beside our destination IP address, and we can rename this. So let's edit column, and we can just change that to source. All right, there we go. And that's a simple way of adjusting your dashboard, adjusting columns for more visibility. And in other videos, we'll be adding more columns for specific things that we're looking for in a packet capture. But this is just a general overview of how to add columns. Now let's look at the time. If we look at the time, this time format is not really doing anything for us. We can't really determine anything. Right now, if we look at view, we go to view and we click on time display format, it looks like it's just showing us in seconds, right? And this is totally fine. Like if we're just looking at, if we're not really caring about time, that's totally fine. But if we're doing some specific kinds of analysis, we want the time format to be in a particular format. So for example, let's say we want to see the date and the time. we want to see the time of day, or we want to see to a particular degree, maybe to the seconds, to the tenth of a seconds, to the milliseconds. We can specify it here. But today, I'm just gonna choose a generic time format. This one looks pretty okay. So this UTC date and time of day. So we can click that, and here we can see the date, and we can see the specific time of the day. So this is a great way to kind of have a better view of time, especially if you're doing like actual security analysis. You want to have specific time. You want to know the specific time that something happened in the network. This is a great way to have that kind of view and visibility for your packet capture. But this is a general overview of how to use Wireshark for specific things, how to download Wireshark, how to install Wireshark, how to add and remove columns, and just customize your dashboard for more visibility, especially if you're doing security analysis. Today we're just going to be going over basic filtering, how to filter, how to save a filter, different kinds of filter operators, and just the basics of general filtering that you should know for Wireshark. So I'm actually going to start with analyzing a static packet capture that I have on my device. So if I do ls, you can see this packet capture right here in my home directory. I can use the command Wireshark and the name of the packet capture to open that packet capture, and Wireshark will open the packet capture for me, and we can start with that. All right, so in Wireshark there are a bunch of filter operators that are used, and it's pretty I'll say pretty similar to different tools that use filter operators. So you have your normal equal to, so if you're trying to say something equals to something, we can use the equal to operator, or the equal to operator. So they usually come and you can use either of them. So we can say let's say TCP port equals 80, right? That's HTTP traffic, right? Or we can say TCP port EQ 80, right? And we can see that. And then we can use not equal to, right? So we can say, for example, equal to, instead of EQ, we can say exclamation mark equal to. So we want to see packets that did not have a TCP port of 80, right? That's what essentially that is. And we can also say NE to replace that. And then there is the AND operator. So let's say we want to do TCP port equals 80 and IP source, which is essentially a filter for source IP, equals 10.10.100.139. IP source TCP port equals 80 and IP source TCP port equals, I had a typo right there, TCP port equals 80 and IP source equals 10.10.100.139. All right, so this kind of joins these together. So any packet that has a TCP port of 80 and a source IP of 10.10.100.139. What if we want to see TCP port 80 and packets that do not have an IP source of 10.10.100.139? We can just replace that with this, and we will see packets that have a TCP port of 80 and did not have this source IP. All right, and then there's also the OR operator. So we can replace this with OR. Let me space that out. So just put 80 or, so we can say any packet that has a TCP port 80 or or does not have a source IP of 10.10.100.139. And we can also use this two pipes to represent OR as well. So either OR as an or two pipes for that. There are also operators like greater than GT or the greater than symbol. There's also the less than symbol, which can also be replaced with LT. There is the greater than or equal to symbol, which can also be replaced with GE. there is the less than or equal to symbol, which can also be replaced with LE. All right, so that's just the basics of how to filter for traffic with Wireshark. So there are some basic filtering options you should definitely know, like of course IP source, which we just went over, right? IP source. There's also IP destination for the destination IP. There is also we can also say IP destination host, which is almost the same thing as IP source. As you can see here, Wireshark already gives us a suggestion for that, and Wireshark is pretty great at giving suggestions for filters. We can also specify for specific protocols, so we can say TCP, and we'll see also the TCP traffic. We can say HTTP, we'll see also the HTTP traffic. Let's say we have some FTP information, we would see FTP, but we do not have that. We can say DNS. We would see also DNS traffic. We filter for DHCP. So any form of protocol you can think of, you can definitely filter. And I'll be doing more specific videos for certain protocols that are going to be important for our traffic analysis. And for example, if you wanted to, specify, let's say you want to do a filter for DNS, right? DNS is, we can use just the name DNS. We can also specifically say UDP port 53, right? Because we know DNS is 53, and we're gonna essentially get the same result. What if we wanted to filter? We do not want to see DNS traffic. We'll say not equal to 53, right? Or we can say not DNS. So we can say not DNS, all right, like that. Let's say we wanted to combine two queries, right? We'll say we wanted to see UDP port 53, which is DNS UDP port 53, and we can see Wireshark gives us the option to filter back with what we had before. So I'll click on that, and we also want to specify for ARP, any form of ARP communication in our network. So we can see there is, we said UDP port not 53 and ARP, so we're not going to see any data because like we don't have any packet that it's this specific filter, right? Well, let's say we said OR, right? We used the OR command. We would see some data because we are specifying for not 53 or ARP, right? We can also replace that OR with the two pipes, and we'll see that. Let's say we wanted to do UDP port not 53, or let's actually say UDP port 53. So let's say we wanted to see DNS traffic, and so DNS traffic and not ARP traffic, right? So we'll say and we can use parenthesis to segment of what we do not want to see, right? So that way we have a better structure for our query. All right, let's say we wanted to see DNS traffic, but we do want to see ARP and we do want to see HTTP as well, right? We can add that to the query and we'll see all sort of DNS traffic, but we will not see ARP and we will not see HTTP as well. So with this knowledge of the basics of the filtering options, you can create more advanced filters to specify what kind of traffic you're looking for in Wireshark. And this is just the beginning. Like once you start doing the analysis and you start looking for things, you want to kind of weed out information that is not important for your analysis, and just focus on what is you essentially need. And also you can also save your filter options. So for example, let's say there's a particular filter you use all the time for your analysis, you can save it. So let's say, for example, we use this particular filter a lot for analysis. So we have it filtered. We can just click this plus button right here and we'll say frequently used. We can name it anything you want. So let's say frequently used, right? And you can see it would be saved right here on the top right. So let me just clear this out. So this is just basic, right? This is just we don't have any filter right here right now, right? So if we click this frequently used, it's going to populate our bar, our filter bar with the frequently used filter that we saved. So to confirm that one more time, let me just say I filter for HTTP, right? We only see HTTP data. right, we can go back and click for frequently used, and we will have that filter in there once again. So that's the basics of filtering. Another way you can also filter is, for example, let's say you're looking at this packet capture and you wanted to filter for something specific. So let's say we're looking at this and we're looking at something really interesting in one of these headers, and we kind of stumble upon this source. Okay, let's say for example we stumble upon this source that's a HLP device, and we want to filter for every packet that has this HLP device. We can right click and then apply as filter selected. So it will create a filter for that particular option that we chose to see in our packet capture. We can also apply as filter for not selected. So it would say not stat. So it would use that, it would negate that filter that we use so that we do not see, we see traffic that we do not see any traffic that has this particular option or this particular value in it. So that's also a great way to filter for traffic in Wireshark. We can use literally any of these options that we have in the packet headers as filter options in our Wireshark just by simply right clicking and either applying as filter, selected, not selected, and you can also go ahead and play around with these other ones and figure out what they do. But that's just the basics of how to filter for traffic in Wireshark. So definitely try to play around with it. So start Wireshark in your home network and just start trying to filter for certain type of traffic, maybe HTTP, DNS, and see what's going on in your home network, and just build more complex filters, and that way you get better at using Wireshark for filtering. So I'm currently analyzing this packet capture from malware-traffic-analysis.net. Like I said, today we're going to be talking about statistics, and this is what we're going to be looking at. There's a bunch of options under statistics, and statistics essentially help us to have a really great overview of everything that's going on in the packet capture. So it's helpful in different statistics about the traffic in the capture file, such as like the percentages or the proportions of the protocols, the amount of bytes transmitted to different hosts, and the IP addresses of all the hosts. And it can also be great in terms of identifying some potential security events in our network. So we can possibly identify exfiltration vectors and identify exfiltrating hosts based off the network usage that we can detect from the statistics of the host. So let's just dive right into that. So like I said, we can see statistics has a bunch of options, and we're going to be specifically looking at protocol hierarchy, conversations, and endpoints. Those are the ones that are very, very important to us. You can definitely check out the other ones and look into them, but for this specific video, we're going to be looking at protocol hierarchy, conversations, and endpoints. So starting with protocol hierarchy, this essentially displays the percentages of the number of bytes or packets in a protocol conversation and compares it to the entire traffic, the entire packet traffic. So and this is organized in layers. So if you're familiar with the OSI layers, you're familiar with the different layers of the OSI model, and this arranges it from top to bottom, so from layer 2 to layer 7. So we can see this is the frame, and this is the Ethernet header, and then we have the IPv4, and then we have the UDP information as well. So in the UDP packets, we have all of these protocols. We have NTP, which is network time protocol, NetBIOS name service, LMNR, DHCP, DNS, and more data. And then we also have the TCP packets as well, and then HTTP. So we can see how that is all set up, and we can see all of the information about the packets. So the percentage of the packets, the amount of packets, the bytes that we transmitted in the packets, the percentage of the bytes that were transmitted in the packets. So it gives us a really, really detailed overview of all of these different protocols, as the name implies, protocol hierarchy. So for example, if we wanted to check a specific protocol, like traffic for a specific protocol in the packet list, we can just simply right click on that protocol and apply as a filter. So let's say we wanted to specifically filter for DHCP, so we can click on that, right click on that, and then apply as a filter either selected, which will show us all of the information that is DHCP related, or if we say not selected, that means we want to see all of the information that is not DHCP related. So we don't want to see any form of DHCP traffic with the not selected option. And in Wireshark, we automatically create a filter and apply that as the display filter. So let's just choose non-selected for this DHCP, and as we can see here, it essentially just filters for DHCP in the packet capture. So in terms of security analysis, the protocol hierarchy window can easily identify data exfiltration through the use of unusual or unused protocols. So if we're seeing some sort of network traffic or some sort of communications with unusual protocols or unused protocols, then that is some suspicious activity that we definitely want to investigate. So for example, if we're noticing a very small portion of, say, FTP traffic in a large network that does not use FTP, that there is no reason why FTP should be used, it might be worth checking that out, because to ensure that that traffic is legitimate, because that could be a way or a vector of data exfiltration. So that's definitely something to keep in mind. So that is that for protocol hierarchy. Let's just look at conversations. Now, conversations is also a really great one. It provides a wealth of information about the traffic, with including like all the different hosts that are communicating the traffic, ports, the packets, the bytes, and all of that stuff. So with this, we're able to identify a bunch of things. So we can look at MAC addresses, so all of the MAC addresses that exist in the packet, all of the IPv4 addresses, all of the IPv6 if there are any, of the TCP communications, all of the UDP communications, and also the volume of the traffic, the volume of the traffic that exists between the communication between the source and destination host, or the source and destination IP addresses. So this is a really great overview of that, and it's and a great way to use it is to like sort from top to bottom. So for example, here if we click on packets, here we can see we are able to sort it from lowest to highest. If we click that again, we can sort from highest to lowest. So we can see there's a lot of there's so many packets going between this source IP and this destination IP. So if this was something that was unusual for us, we could also apply this as a filter. So we can say apply as filter selected, and we can say A to B, which is source IP to that destination IP, either back and forth, or just address A to address B, or address B to address A. So we're just gonna keep it simple, and we'll just say address A to address B. And if we pull that down, we can see that it created a filter for that. So IP source is that, and IP destination is that. So all of the packets that have the IP source of this and the IP destination of that is what it filtered for. So we're not going to see any form of any unrelated traffic is not going to be shown in this filter that we have created from the conversations that are going on in the packet capture. So this is also very useful for investigating data exfiltration attempts, because we can use it to identify an attacker's IP address. So if a host has been transmitting many packets and many bytes to an unidentified IP address or suspicious IP address without receiving many packets back, that could be some sort of exfiltration. Or we can also use it to detect some sorts of beaconing traffic from internal hosts to a command and control server, just by trying to find irregular forms of communication between the host and probably some sort of malicious IP address that it might be beaconing to. So that is a overview of the conversations option in Wireshark. So let us close that out. And the last one we're going to be looking at is endpoints. So endpoints is essentially showing us all of the different hosts that appear in the packet capture and the amount of packet or bytes that they sent or received in the packet capture. So we can use this to like sort the hosts by the network activity, either by the transmission packets or the amount of packets that they sent or received, or even both of them. So we can also see all of the Ethernet, all of the MAC addresses in the Ethernet header. We can see all the IPv4 addresses, all the IPv6, all the TCP communication, all the UDP communication. So we see all the endpoints, right? So, and we see here it's not, from source to destination or from destination to source. It just lists all of the individual IP addresses that are in the network and all of the information pertaining to them. So, for example, let's say we wanted to sort by the amount of packets that the IP address is sent. So let's say from lowest to highest, or maybe from highest to lowest, or the amount of bytes, we can sort by that too, and a bunch of other different things that we can use to filter for that. So for example, we're looking at this particular sort by high to low. Okay, so we're looking at this particular IP address and it's sending the most packets and the most amount of bytes in the network. So you might want to investigate that, right? And we can just like based off of that filter as well as we've done in the other ones. So we can filter for all packets that have this particular IP address, and then we could create a filter for that in our Wireshark. So it shows this is showing all of the packets that have this particular IP address, whether it be source or destination, and that way we can start doing some sort of analysis, whatever form of analysis we choose to do with that. So that's kind of a high level overview of the endpoints option in the statistics tab of Wireshark. So once again, a brief summary of the statistics. Statistics essentially give us a holistic view of the packet capture, because we have tons of packets here. If we look at this, we have over almost 10,000 packets here. So this just gives us overview of everything going on in the packet capture. So like percentages of the host, the protocols, the bytes, the packets, and all of that. So that way we can easily kind of detect anomalous communications or things that just should not be there, or things that we do not expect to be in our packet capture. HTTP data is something that you're going to be spending a lot of time on if you're going to be analyzing packet capture. So having an understanding of what you can do with HTTP data is really important. And so this video is going to cover a ton of resources that can help you in terms of analyzing HTTP data in a packet capture. So let's just get started. So first things first, we can easily just filter for HTTP, and here it's just going to specify only HTTP packets. So we can see all the protocols here are all HTTP. Okay, so that's one way. Another way is we can specify for HTTP using the port number. So we can say TCP port equals, as we learned before, using the equal operator, 80, right? So we're not just seeing HTTP data, we're also seeing TCP data that's also web traffic. So this covers beyond just the HTTP data, also covers the TCP data as well. So that's another way. We can also choose to do maybe HTTPS if we're looking at that, and here we can see it's all TCP and TLS stuff because it's all encrypted. So that's the basics of just specifically filtering for HTTP data. Now, in HTTP data, we can find so much stuff. All right, so like I said, there's so many capabilities that Wireshark has for analyzing HTTP data. We can filter for user agents. We can filter for header information. We can filter for cookies. We can filter for response numbers. We can filter for status codes. We can filter for HTTP response, HTTP request. We can filter for the HTTP referrer. We can filter for file data. We can filter for we can filter for so many things. So let's just get into a couple of those things we can filter for in HTTP data, and we will start with HTTP request method. So that's a pretty popular one. We could just say HTTP request, and we're going to see all of the HTTP packets that have some sort of request. So the request could be a post, it could be a put, it could be head, it could be get. So if we follow this TCP stream, we can see request method. We might not be able to see that from here, but if we look at the header of the HTTP packet, so we look here, we can see different parameters. So we see this right here is the request method, if I'm not mistaken. So follow, actually apply as filter, selected. Okay, it's gonna, that's way beyond what we're looking at. But okay, this is what we're looking for, the request method. So if we dig down a bit more, we can see a request method, and this is specifically a get request. So if we apply this as a filter, it will only show us all the requests that are get requests, right? And we can see that here. Let's say we wanted to look at post requests, right? So we can replace that get with post, and it will show us all the posts. Let's say we want to look at head, we would also replace that, and it will show us all of the head requests. So those are the different ways we can filter for the HTTP request method. So we're trying to see some sort if our client is sending information out to a server, we can use the post. If we're trying to see what information our client is getting from a server, we use get. So for example, if we're trying to analyze maybe possible beaconing activity, we can try to filter for HTTP post data, because we see that our client or multiple clients are beaconing out to a command and control server if it's some sort of beaconing activity. All right, that's that with HTTP request method. We could also filter for specific things in the HTTP file. So let's actually do this with a live packet capture. So let me fire up Wireshark here. So I'll do sudo Wireshark, enter, and I have to type my password. All right, so I'm going to. It's like there's nothing going on here. There should be some sort of optic. Okay, there we go. There we go. We can see traffic going on there. So let's filter and let's start the capture, and we can now navigate to this website, and it's called Web Scraper Testing Ground. So it's a HTTP website, meaning it's not secured, so it doesn't have the S, doesn't have a certificate. And let's see if we had that captured in our packet capture. And what we'll do is we'll go back to that browser, and then let's just reload this page and see if we get any data. Okay, there we go. We see all of this HTTP data, and it's going towards this particular IP address, 185.221.154.249, and if we follow that that TCP stream or HTTP stream, whichever, we're able to see all of the information going back and forth. So we can see it's like they started with a GET request to testing ground web scraping.pro, which is what we were which is the website we did. So let's just close that out. So we see that our HTTP traffic is being captured. Now, what I want to show is specifically what we can get with just clear HTTP traffic. So in this web page, we can easily put in like some credentials. So let's just put in some fake credentials. So admin, and we'll just say password, you are hacked, and enter. All right, awesome. So let's go back to our packet capture, and there's a ton of stuff here, right? And we are trying to find our credentials that we just put in, right? So let's filter for HTTP and filter for file data. So it's essentially saying the HTTP file data, right? Which is, whatever a specific parameter in the HTTP file data that we're going to specify for. So HTTP file data contains, so we can filter for anything. We can filter for, say, we entered admin, right? So let's put in admin, and we can see there are 2 packets with that. We could also specify for maybe the password we put in, but sometimes we don't even know. Let's say we're probably analyzing this packet capture, and we don't even know that somebody has put in a password. Let's just filter for password. There's probably a password field in there somewhere, all right? Okay, there is not, but that is one way we can filter for HTTP, traffic. So if there's like clear text stuff going on in, the network with credentials, we can filter for HTTP file data contains so and so. Like, for example, we already know that, we put in the password as the username as admin, so we can specify for admin, and we will find the packet capture that has that admin. So if we follow that TCP stream or HTTP stream, whichever, we can see the back and forth communication, and when we look here, we can see where we entered our username and password. So user, admin, and password, you are hacked. So that's that's also part of what you can filter for in HTTP. We can also filter for the user agent. You can say HTTP user agent, let's say contains. So let's say we're looking for maybe Mozilla, so Mozilla, and we're gonna see all the user agents that contain Mozilla. Obviously, I'm using Mozilla, so you can see all of the HTTP data. We can also, let's say we're analyzing like malware or maybe an exploit kit, and we know there's a particular user agent that is familiar with that malware exploit kit. We can specify specifically for that. So those are like some of the things we can specify for, it's HTTP traffic in Wireshark. There's a ton of things you can specify for, a ton of things you can specify with HTTP. So I recommend you play around with that, and also you can just go into the HTTP header and right here, and you can look at things you want to maybe specify for, you maybe want to filter for, and just add them. Let's say you want to filter for a referrer, or you want to add the referrer as a column. You can definitely do that just by right clicking either apply it as column if you want to add as a column, or apply as a filter if you're looking to apply it as a filter. So there's a ton of things you can do with HTTP. You can also get the entire web page just from HTTP data. So if we look here and let's see HTTP, let's filter for HTTP file data contains HTML. I want to see all this stuff that contains HTML. So let's look at this and let's follow HTTP stream. All right, cool. So let's copy this HTML code right here. Right, this HTML code is exactly the same thing from the web page that we opened, the scraping web page that we opened. So, oops. Okay, let's copy that. All right. Copy too much. All right, there we go. Start from here, and if I copy that, let me use copy and open a command line. Let me open a new terminal, and let's do cd desktop, and let's do nano sample.html, right? And let me paste that HTML code in here, right? And we can see it's all HTML code. All right. Looks like it might contain some JavaScript, but yeah, it's all HTML code as I can see. And then I can do Ctrl+X and save. Yes. All right, cool. So we have this HTML file open. So if we head over to our desktop and click on sample.html, we can see it's almost the same thing as this particular what we're seeing here. It's probably because we're not able to access all of the CSS files, and we're not linking the CSS files to the HTML data. But if you look at it, it's essentially the same thing as what we have here. It's just that this looks better and has the colors and everything. So that's one powerful thing we can do with filtering for HTTP traffic. If everything is not encrypted, we can pull the code from the packet capture. We can pull the HTML code from the packet capture and reconstruct it, and also and see what the user saw when they opened the web page. So for example, if we never knew what the user clicked, but we have the HTML data, we have the HTML code, we can put it put it in a file and open it and see what the user saw at the time that they clicked the link. If it's for example, we're analyzing a phishing link for example. So yeah, like I said, there's a ton of things we can do with HTTP, and that's like why I dedicated a specific video just for that. So definitely play around with it and find different ways that you can filter for different kinds of HTTP traffic. So I'm going to be going over 3 major ways that you can use to find host and user accounts in a packet capture. Because if you're doing security analysis with Wireshark, you're definitely going to be looking for hosts, compromised hosts, infected hosts, or user accounts. Maybe trying to find a user that might have clicked a link, or that might have accessed the website, or authenticated to a domain server, or something like that. So this is definitely going to be really, really important if you're going to be doing security analysis. So with all of that said, let's just get started. All right, so the 3 major ways we're going to be using to filter for hosting user accounts is going to be through DHCP, and second one is going to be NetBIOS name service, or NBNS, and the last one is going to be through Kerberos. So let's start with DHCP. So let's start with just filtering basically for DHCP as a protocol, and here you can see we have just 2 packets covering DHCP. So let me just kind of close this down to how it would actually look when you open a DHCP packet for the first time. So, all right. So when you filter for a DHCP packet for the first time, you will be greeted with something like this. And next thing you do is to head over into the DHCP header right here, and you open that, and then scroll down to the host name, which is option 12, and there we can find the information about the host, which is Stephanie PC in this packet capture. And there are a bunch of other things that you can also find in the packet capture, but the most important thing here to us right now is the host name. So DHCP works in a process called, it's short for DARA. So it starts with the discovery, and then it goes over to offer, and then from offer to request, and then from request to acknowledgement. So that's like the 4-way process that DHCP works. So we're usually trying to find information at the third part of the DHCP process, which is at the requests, or in some cases we might have it as inform in a packet capture. So definitely keep an eye out for DHCP inform or DHCP request. That's where you're usually gonna find the information you need for your host. So just in case you have a packet capture that has just more than this, because you're definitely gonna have packet captures that are gonna have more DHCP information. So keep an eye out for the ones that have the requests or the inform, because that's where you're gonna find the information you need for your host. All right, so that's the first way we can use. Another way another alternative to DHCP filtering is through BootP. So if we filter for BootP, we're essentially going to get the same results. So this is definitely another way we can use. This is the Bootstrap protocol, and it's kind of an alternative to filter for DHCP traffic. So if you're filtering for DHCP traffic and you're not really finding what you're looking for, definitely try to use the BootP filter to find DHCP information about the host you might be looking for in your packet capture. All right, so now we've gone over DHCP trying to filter for DHCP, and now we're going to look at NBNS, also known as NetBIOS Name Service. So DHCP works with leases, right? So the DHCP server leases an IP address for a certain period of time, and this lease can expire or be renewed from time to time, and the packet capture might not include that. So we can also use alternatively, we can use NetBIOS Name Service to find Windows and macOS devices, and we can simply just do that by just filtering for NBNS. And here we can see there's a ton of NBNS packets in our packet capture. But what we're really concerned about is the host. So as you can see, we already see some information here. So we see Stephanie PC and we see a work group. Like I said, we're more concerned about the host right now. And when you first open a NBNS packet, so this is what it will look like, and then you drill down into the NBNS header and then into the additional records, and right there and there you would find the name. So this is the name of the host, which is Stephanie PC. And you can also see the IP address, which is 192.168.137.25. All right, so that's essentially the gist of it for NBNS. And the last and final way that we can filter for hosts or user accounts in our packet capture is through Kerberos. So Kerberos is a Windows authentication protocol. So if you're filtering for traffic in like a Active Directory environment or a Windows environment, you're very, very likely to find some sort of Kerberos traffic if users are trying to authenticate to like a domain server or something like that, or a domain controller. So the way we filter for Kerberos traffic, and disclaimer, this packet does not have any Kerberos traffic, but we will be looking at other packet captures later on this channel that will definitely have Kerberos traffic. So definitely keep an eye out for that. But the filter we use to filter for Kerberos traffic is Kerberos canonical name, which is short into CNAME, the typo, CNAME string. Kerberos CNAME string. All right, there we go. So you usually filter for this, and then you would find packets that have Kerberos traffic, and you would usually find them somewhere here. And just a rule of thumb to know, the host names usually end with a $, and the usernames usually do not have a $. So Kerberos kind of kills two birds with one stone, because as it shows you the host names and the usernames. So once you look at the traffic right here, you would see right here in this part of the screen, this info, you would see the different hosts and user accounts. So you can easily identify the host by looking at the names that have a $, at the end of them, and you can identify usernames by the ones that do not have a $, on them at all. So that's easy way to find host and user accounts in your packet capture. So once again, just to reiterate, we can use DHCP. Alternatively, we can use BootP. And just in case we're not able to find our DHCP information, we can use NBNS. And finally, we can use Kerberos CNAME string. All right, so those are the three simple ways you can use to find user accounts and hosts in your packet capture. The packet I'll be using for this video is going to be from Chris Sanders' GitHub, and it's going to be called the DHCP. Where is that at? It's going to be called the DHCP No Lease Initialization PCAP. Just a quick information about Chris Sanders. He is a cybersecurity author, analyst, and instructor. Also, if you know the Practical Packet Analysis book, he is the one who wrote the book. I actually recently just finished reading that book, and that book is a really amazing book for anyone who wants to to learn more about network analysis, Wireshark, or just basics of networking in general. So I highly recommend it if you're looking to learn any of those skills. I'm also currently reading his Applied Network Security Monitoring book, and I will be definitely giving my opinions about it when I'm done with it. So, like I said, we'll be getting the packet capture from his package repository on GitHub. But before I get into it, I recommend checking out his publications. So he has a bunch of papers and presentations that he's done over the years, which are gratefully free on YouTube. So I definitely recommend checking some of them out. They're really, really great talks, especially if you're new to the industry. He has a lot of great insight that I think is really, really, really beneficial for new security analysts and also experienced and seasoned security analysts. So if you're watching this video and you're a new security analyst or an experienced security analyst, I recommend you check out these publications. I think you're gonna at least find something valuable in any of the publications you watch or you read. So with all of that said, let's just dive right into the purpose of today's video. All right, so we're going to be looking at this DHCP packet capture, and before we go into that, just a brief definition of what DHCP is. DHCP is an acronym for the Dynamic Host Configuration Protocol, and DHCP is an application layer protocol. So if you're familiar with the OSI model, it's essentially at the very top of the OSI model, and DHCP is essentially used to automatically obtain or assign IP addresses to hosts without an IP address. So a lot of times when hosts just are new on the network, they might not have an IP address, so they use the DHCP protocol to obtain IP addresses, or the TCP server uses the DHCP protocol to assign IP addresses to the host or the device without an IP address. So DHCP originally originated from the BootP protocol, the Bootstrap protocol, and it's essentially a sophisticated and a more updated version of the Bootstrap protocol. And we can still find the Bootstrap information in DHCP. So we can see right here, the very first line in the DHCP header packet is the message type is a boot request. So that's just some history information about DHCP, and we can filter for DHCP using just the DHCP filter. So we can just say DHCP, and we can also filter using the BootP, which is the equivalent for the Bootstrap protocol. So those are the two ways we can filter for DHCP. So DHCP uses UDP port 68 for the client and UDP port 67 for the server. So as you can see here, the very first packet shows a source port of 68 and the destination port of 67. So the client is using the port 68 and sending a broadcast message to the server over port 67. And we can also see that DHCP is a UDP protocol. So it's a connectionless protocol, and we'll be looking more at UDP and TCP later on in this series. All right, so DHCP works, the initial process of DHCP works in a four-way step. As you can see, we have 4 packets here, and the very first one is a DHCP discover, second one is a DHCP offer, the third one is a DHCP request, and the fourth one and last one is a DHCP acknowledgement. And we'll be going over each of these steps of the DHCP process. But before we go over that, we can see that the 4 steps they come together to form a acronym of DORA. So if you're looking to remember the DHCP process, just remember DORA. So D for discover, O for offer, R for request, and A for acknowledgement. So the very first step, which is a discover, the host sends a broadcast message using the discover packet to the broadcast domain. So essentially sends a packet from this IP address of 0.0.0.0 because it does not have an IP address. So it's using DHCP to send this broadcast message because it needs the IP address. So it's sending this discover message from 0.0.0.0 to over port 68 to the broadcast domain. So if you're familiar with how broadcast messages work, if you're sending a broadcast message, the destination IP address is usually 255.255.255.255. So that is essentially how the communication starts. After the client that needs the IP address has sent that broadcast message, the DHCP server responds back to the client with a DHCP offer message or DHCP offer packet. And this DHCP offer packet has a good amount of information in it. So as you can see here, the DHCP offer packet responds back with right here option offer and responds back with the DHCP server identifier. So if when the client has to respond back to the DHCP server, it knows what server to respond back to. The IP address lease time, as you can see here, for this particular IP address, it's 10 minutes. The subnet mask, so definitely have to have a subnet mask to kind of classify where the host will be in, and then a bunch of other things that are going to be important for the host to communicate on the network. So this is essentially the DHCP server responding back to that client with everything it needs to communicate on the network. Now, the client responds back still with a 0.0.0.0 IP address because it still doesn't have that IP address. It responds back again with a broadcast with a request. So it's saying, hey DHCP server, I would actually appreciate all of that information you send me. So it's essentially accepting the offer that the DHCP server sent it, and finally the DHCP server responds back with an acknowledgement with the requested information that the client asked for, and after that it requests the information it's in its database. So that's essentially how the DHCP process works. So first we iterate that. Starts with the discover, with the client looking for the DHCP server, and then responds back from the DHCP server to the client with the offer, essentially giving the client all of the information it needs to communicate on the network. And then the third process is a request, which is the client responding back to the DHCP server, accepting all the information that the DHCP server sent to it. And finally, acknowledgement, which essentially ends the communication. So as you can see here, these are the different DHCP messages, but we can also have other DHCP messages. Another one could be a DHCP release, which is sent by the client to the server to cancel a lease by releasing its configuration parameters. So if a client no longer wants to use the IP address and the information that DHCP server sent to it, then it would use a DHCP release packet. Another one that we'll see a lot is a DHCP inform. We've also seen that in previous analysis that I've done on the channel. So rather than a DHCP request, we can see a DHCP inform, which is essentially the client responding to a server asking for the configuration parameters it needs to communicate on the network, but the client already has an IP address. So we will be seeing more DHCP inform in our analysis later on in this channel and in other videos. So that's essentially a really high level overview of how DHCP packets work. So we'll be looking at ARP, and the packet capture I'll be using for this video is from GitHub. From Chris Sanders' packet repository, and it's going to be this ARP resolution packet. So let's dive into the packet capture. And before we get started, just to give a brief definition of how ARP works. ARP is short for Address Resolution Protocol, and it's a protocol that's used when an IP address is known but a MAC address is needed. So the IP address is known but we don't know the MAC address. ARP usually works with using one of two packet types. So there's usually an ARP request or an ARP response. So how ARP works is, for example, host A, we have host A and host B in the network, and host A wants to send data to host B, right? So host A knows host B's IP address but doesn't know its MAC address. Because of this, host A decides to send out a broadcast ARP request to all the devices in the broadcast domain, and it tells them its IP address and its MAC address, and then it asks that whoever out of all the hosts in the broadcast domain that has the IP address that it knows to send its MAC address back to host B. So whoever is host B responds back with a ARP response back directly to host A with its IP address and MAC address as requested by host A, and that's essentially how ARP works. So I know that's a lot said, but we'll look at how that works in this packet capture right now. So starting with the ARP request, let's assume that this first device, here PR, is host A and the link is host B. So host A wants to send data to host B, but it doesn't know its MAC address. It only knows its IP address. So this ARP request essentially just says who has 192.168.0.1. Tell 192.168.0.114. As simple as that. That's the summary of the ARP request, right? And if we look at the ARP request packet here, we can see that the sender IP address is 192.168.0.14, which belongs to host A, and essentially is the IP address that host A is telling this host at 192.168.0.1 to report back to with its MAC address. All right, so we can see the response, which is host B replying back to host A, is showing 192.168.0.1 is at this particular MAC address, and we can see target IP address is host A, which is 192.168.0.14. So that's kind of a whole summary of how ARP works. It's not overly complicated. There definitely is a lot more that goes to it sometimes, but this is essentially the gist of how it works. And in the midst of all this communication, after the broadcast is sent, every host or every device that is not host B will drop the broadcast packet. So when the first packet is sent, when the first broadcast packet is sent, only host B, only the host that has the IP address and the MAC address that's required will respond back. Every other host will drop the packets because it does not concern them. They're not the ones that are needed for the communication. So that's a brief summary of how ARP works. We're going to be looking at TCP and UDP as part of our Wireshark series for security analysis. I believe understanding these two protocols is very important and is the foundation for understanding other protocols, ports, and services that are important. Please be sure to like the video and subscribe if you've not, and thank you to everyone who's already subscribed. I truly appreciate you all. Now, what is TCP? TCP is short for Transmission Control Protocol and is essentially used to provide end-to-end reliability for delivery of data or delivery of different packets in the network. Now, TCP is connection oriented. This is a key thing that you have to remember, as we're also going to be talking about UDP, which is a connectionless protocol. Now, TCP essentially keeps track of what is sent and received and ensures that the last bit of information was received before it continues to transmission. And essentially, if you want a more reliable transmission or flow of data, you most likely want to use TCP rather than UDP. Like I said, we will cover UDP in another video. Also, TCP operates at the OSI layer 4. So if you're familiar with the OSI layer model, TCP operates as OSI layer 4, and TCP handles sequencing and error recovery. And ultimately, the purpose of TCP is to ensure that data gets to where it's supposed to go. Now, specifically for Wireshark, we're going to be looking at a TCP handshake. And to explain what a TCP handshake is, simply host A wants to send a TCP packet to host B. So host A initiates a connection with host B using a SYN flag, which we'll be looking at in this video. And then host B replies back to host A with a SYN ACK flag, and then host A replies back to host B with an ACK flag. So that's like what the TCP handshake looks like. So host A with a SYN flag to host B, and host B with a SYN ACK packet back to host A, and then host A replies back to host B with an ACK packet, and then they can start the transmission. Now, let's look at how that works in Wireshark. And we're going to be specifically using a packet capture from Chris Sanders' GitHub, where he has multiple packet captures, and we're specifically going to be using this TCP handshake packet. So let's download that. That should only take a second, and then download. All right, open with Wireshark. Awesome. Now, let's go ahead and analyze our TCP packet. So as you can see here, this 3 packets represent our TCP handshake. So as you can see, it starts with a SYN packet, and then a reply back with a SYN ACK, and then finally an ACK packet. All right, so let's look into what the TCP packet holds. So let's look at the SYN, and we'll open that down, and there's a lot of things that we can see in this TCP header. There's a lot of information. So we can see the source port, which is the port from the initial sender, so host A in this case, and then we have the destination port, which is the destination, which will be host P, and then we have the sequence number, which is used to identify the TCP segment, and this essentially ensures that parts of the data stream are not missing. So we already established that TCP is a connection-oriented protocol, and it has to make sure that all of the information is sent before it starts transmitting more information. So this sequence number ensures that the parts of data are not missing. And then we also have acknowledgement number. So this acknowledgement number is expected in the packet. So the other device expects this number when it's looking at the packet. And then we have the flag, which is really important. There are several TCP flags, but the main ones for the TCP handshake are the SYN, ACK, and ACK. But there are several other TCP flags that are used for different things, and we'll be looking more at these flags when we look at how scanning works in Wireshark. So other flags are the URG flag, there's push flag, PSH, there's a reset flag, which is RSD, which we'll also be looking at when we look at the TCP teardown sequence. So that's really a really important aspect of the TCP header, the flag. So keep that in mind. We also have the window size. So the window size is essentially the size of the TCP receiver buffer in bytes. So this number is in bytes. And you can use this window size for a couple of things. Window size can be used to identify like operating systems or identify maybe scanning engines and different things like that. So this is also a really important part of the TCP header. And then we have the checksum. So the checksum essentially ensures that the contents of the TCP header and the data are intact upon arrival. So like we already established, TCP is a connection-oriented protocol, so it has multiple things in place to ensure that data is successfully transmitted. So this checksum is part of those things. Now, the this urgent pointer is if the URG flag is set. Like I mentioned, it's one of the flags that you can possibly see in the TCP header. If the URG flag is set, this field is examined for additional instructions for where the CPU should begin reading the data within the packet. So that's kind of what this urgent pointer is used for. And then we have the options, and these options are just like various optional fields that can be specified in the TCP packet. So those are the main components of the TCP header, and we can see how the TCP handshake works. So it starts with a SYN to the destination. So host A is 172.16.16.128, and host B is 212.58.226.142. So host A sends a SYN packet to host B, and host B replies back with a SYN ACK, and then host A replies back to host B with a ACK packet. And then after this handshake is completed, then the actual transmission can start, and the host A can start sending information to host B. Now that is the TCP three-way handshake. This is a really important thing to know, because it's something that you need to understand in different aspects of security, apart from just analyzing packet captures. There's also a question that comes up a lot in cybersecurity interview if you're interviewed for cybersecurity positions. So definitely keep that in mind. So that is the TCP three-way handshake. And there's another thing, which is a TCP teardown, which I don't see being talked about a lot for some reason. So it's kind of the reverse of the TCP handshake, because it's like when the transmission is about to end. So let's kind of look at how the TCP teardown works. And once again, we'll be using the packet capture from Chris Sanders' GitHub, and we'll be looking at TCP teardown, this one, and download, open with Wireshark. Awesome. So the TCP teardown is essentially, like I said, the reverse of the TCP three-way handshake. So the three-way handshake is usually when host A wants to initiate a connection to host B, and the teardown is when the connection is about to end. So when the teardown is about to happen, host A sends a FIN ACK packet to host B to end the connection. So that's like the first communication saying, oh, it's time to end this connection. And then host B replies back to host A with two packets. So the first packet is an ACK packet, right, to acknowledge that, okay, I'm happy to end this connection, and then a FIN ACK packet after that. So it's two communications, two packets from host B back to host A, and then finally host A replies back to host B with an ACK packet. So the commonality between the three-way handshake and the teardown is it usually ends with an ACK package, or the ACK stands for acknowledgement or acknowledge. So that's like the commonality between the three-way handshake and the teardown. So starts with a FIN ACK for the teardown and a SYN for the three-way, and then in the middle we have the ACK and FIN ACK for the teardown. So two packets for the teardown, but for the three-way it's one packet with only a SYN ACK, and then finally both the three-way and the teardown end with an ACK packet. All right, so that's how the TCP teardown works. And once again, the TCP teardown is used to end a connection. Now, another TCP flag that is also important is the reset flag, or you would normally see that as RST in place of, rather than ACK or FIN ACK, you would see an RST. And it's used to indicate that a connection was abruptly closed, or there was a refusal to the connection. So keep in mind when you see an RST packet for a TCP protocol, it's used to indicate that the connection was abruptly closed, or the destination host refused the connection attempt. So a little bit more about TCP. There are 65,535 ports available for TCP, and the first 1024 are the standard ports. So the first 1024 are the standard ports, and 0 is actually reserved. So I guess from 1 to 1023 are the standard ports. So your regular ports that you normally use. So DNS 53, HTTP 80, HTTPS 443, FTP 21, SSH 22. Those are your standard regular ports that you normally see in normal communication, and we have some that deviate from that, like RDP, which is 3389. And then we have the ephemeral ports, which are from 1024 through 6535. So in all we have 6535, and the first 1024 are the standard ports, and then from 1024 down to the last 6535 are called ephemeral ports. And these are essentially used because during a transmission, only one service can communicate on a port at a given time. So if we have, let's say, host A communicating with a host B over a particular port, it can only communicate on one port at a given time. So the operating system, or the host, selects a port at random out of these one of these ephemeral ports between 1024 and 6535 to make the communication unique, so that we're not using the exact same port for the given communication. So the ephemeral ports are that many, so that the host can essentially pick any of those source ports at random for the transmission that it's working on at that point in time. So we've kind of covered the main things required for TCP communication. Once again, to reiterate, the basics of TCP is it's essentially used for reliability. It's connection oriented, so it has different things in place in its header to ensure that data is transmitted successfully. Now let's look at UDP. What is UDP? UDP stands for User Datagram Protocol, and it's aimed specifically at speedy transmissions. And one of the major uses of UDP protocol is for streaming audio or streaming video, because we can deal with losing a little bit of data and maybe some drop packets here and there, and maybe during the transmission we could deal with maybe a little bit of latency. But what we have to keep in place is the fact that the stream has to continue. So UDP best serves that purpose. So UDP is a best effort or connectionless protocol because it does not formally establish or terminate connections like TCP. When we looked at TCP, we saw that there were different measures in place to ensure that there was an establishment of communication before packets could start transmitting. But UDP doesn't do that. It's not reliable, but it's best effort. So it does its best to ensure the protocol, but it wouldn't go as far as TCP to put all of these different measures in place to ensure that there's communication. So it basically doesn't care. So any application that uses UDP has to take special steps to ensure that data is reliably transmitted when there's a need for transmission. So let's quickly look at what a UDP header looks like. Once again, we're going to be using the packet from Quisander's website, and we'll be looking at UDP. So let's look at this UDP DNS request. And if you didn't know, now you know that DNS works using the UDP protocol. So UDP protocol is not as complicated as the TCP protocol because it doesn't have all of these measures in place to ensure a successful delivery or successful communication. So we can see here the UDP header is very sparse. So just enough information for the packet to go from point A to point B or from point B to point A. And you can see here there are no flags, there's no SYN, there's no ACK, there is no reset, none of that. There's just enough to get the information from point A to point B. That's all it needs to do. So let's quickly look at what we have in the UDP header. So UDP, we have the source port, which is the port from the original sender, which was used to transmit the packet. And then we have the destination port, which is the port towards the destination host to which the packet was transmitted to. And then we have the packet length, which is the length of the packet in bytes. And then finally we have the checksum, which is used to ensure that the contents of the UDP header is intact upon arrival. We also saw that in TCP there was a checksum for this the same exact reason. So like we've seen here, the UDP header pretty sparse because of the way UDP works. And to kind of cover all of that once again, UDP is aimed at speedy transmission, so it basically doesn't care, and it's best effort, so it does its best to send information from point A, point B. It doesn't, make the effort to formally establish the communication, which is the key difference between it and TCP, which makes all of these efforts to ensure that there is an established communication, an established transmission before it starts sending the packets needed for communication between host 1 and host 2. And all of these are really, really important because we're going to be looking at how scanning works in networks with Wireshark. So understanding how all of these different protocols work is going to be important in analyzing scanning packets, because we can see the difference between maybe a TCP scan or a TCP SYN scan, or maybe a UDP scan as well. So this is really important information, so keep all of this in mind. So with that said, that's the end of today's video. I hope you enjoyed this video. I hope you understand the differences between TCP and UDP. I hope you're also able to use this in other things, like maybe interview situations where you're asked to explain TCP or explain UDP or explain the difference between TCP and UDP. This is going to be a brief overview of the ICMP protocol, how it works, and what it looks like in Wireshark. In the last couple of videos, we've covered some lower layer protocols, including ARP, TCP, UDP, and now we'll be ending that list with ICMP. This is also the second to the last video in this series, and I'm very excited for how far this series has come, and I'm looking forward to more series like this where I break down a particular tool or topic and explain everything I know about it. I also appreciate everyone who has been following this series so far. With that said, let's dive right into today's video. Please be sure to like the video and subscribe if you have not, and thank you to everyone who's already subscribed. subscribed. I truly appreciate you all. Now, what is ICMP? ICMP stands for Internet Control Message Protocol, and it's generally used to provide information about a device's availability on a network, or as most times, the first step of troubleshooting. So if you're in IT or networking or security, you would know that most of the time, the first step of troubleshooting a device or a host is to usually ping the device. So ping is a tool that uses the ICMP protocol to test network connectivity or for troubleshooting. So if you're trying to find out if you can connect from host A to host B, you probably will be using a ping to kind of find out if that host is available or if you're able to connect to that host. So that's kind of one of the major tools that uses the ICMP protocol, and it's kind of one of the major things that sums up what ICMP does. So basically, ICMP is generally used for network troubleshooting, and it generally is trying to see if a host is online or the network status of the host. So if the host is online or if it's asleep or something like that, you can use the ICMP protocol to see if the status of that host at that given time. So we're going to be looking at how an ICMP header looks, and a couple of things in the ICMP protocol, and just a brief overview of the ICMP protocol, like I said at the start of the video. So we're going to be getting our packet capture from Chris Sanders' website. Okay, so as you can see here, there is a bunch of like ICMP packets. So we see 1, 2, 3, 4, 5, 6, 7, 8. So let's kind of dig into the packet and see what is going on here. First of all, we see it's echo ping. So this is obviously like host, the source host pinging the destination host. So 192.168.100.138 was pinging 192.168.100.1. So we see a ping request, a ping reply request, and back and forth till we get to the 8th packet. So before we go into these request and reply, let's look at what the ICMP header looks like. So the ICMP header is pretty simple, not much going on here because it doesn't really need that much to send the ICMP packet to the required destination. So the first thing we see here is the type. So the type is the classification of the ICMP message. So we could either have like a ICMP request or ICMP reply. So ICMP request is usually the one being sent from the source to the destination. So it's trying to query the destination to know if the destination is online. Like we mentioned earlier on, it's generally used for network troubleshooting. So when we send that request to the host, we're trying to see if that host is online or to know the network status of the host. And alternatively, it could be a reply, which is when the host replies back and lets us know if it's online or if it's not. So back to this ICMP header, and if we look here, we see that this device is a compile code and this is a Cisco device. So probably some networking going on in here. All right, so the next thing in the ICMP header is this code. So this is a sub classification of the ICMP message. So in a request, the code is 0, and in the reply, the code is also 0. If we look through the other packets, it looks like all of it is 0. So it could possibly change in maybe different circumstances. Now, the third thing is the checksum. So in the last couple of videos, we've looked at other lower layer protocols, including ARP, TCP, UDP, and now we're looking at ICMP. And one thing coming about all of these protocols is they usually have a checksum. And in this particular case for ICMP, this checksum ensures that the content of the ICMP header is intact upon arrival, which has pretty much been the same purpose amongst the other lower layer protocols we've looked at. Same with TCP, same with UDP. The checksum essentially ensures that the content of the ICMP header or the content of the particular protocol's header is intact upon arrival. So that's one thing to keep in mind. And then another thing here, we have the identifier sequence number. We also saw sequence numbers in TCP headers, which is kind of used to ensure the successful transmission of data from source to the destination. So that's majorly the important things we look at in the ICMP header. We see here the amount of data that was sent from the source to the destination, and it's pretty much the same between the request and the reply. The major differences are usually the type, which will be a request or reply, and then the differences in the values for the checksum or the code or sequence number and different things like that. So it just, as we can see, the ICMP is pretty simple. It's usually either a request or a reply or a response, and the request is usually from the source to the destination, and the response or the replies are usually from the destination back to the source, letting it know that the host is alive or whatever network status that the host currently has at that time. That's pretty much the gist of it with ICMP. Now, how does scanning work? So scanning is usually the first step an attacker takes when they get into a network. They usually scan the network for ports or services that are running on the network, and we're going to be using this particular packet capture to go over how scanning works. Packet capture we're going to be using is this SynScan PCAP, and I have it already open here in Wireshark. So scanning usually allows the attacker to know which targets are alive and reachable, and which ports or services the attacker can begin to start exploiting. There are different kinds of scanners, and the most popular one, you probably might have heard of it, is mmap. So this is one that is used in the command line. There's also a graphical alternative for it, which is mmap, and there are also different kind of iterations of it, but the most popular one is mmap, usually used to scan a network before the attacker then goes on to do other things. Now, there are other types of scanners. There are vulnerability scanners. So Nessus and OpenVAS fall under the category of vulnerability scanners. Necto also falls under the category of a web server vulnerability scanners. But those are the more common ones. But I'm pretty sure there's several other types of scanners out there that you can do more research on your own. So in this video, we're specifically going to be looking at TCP SynScan, or simply a SynScan, which is the reason why I mentioned that if you've not looked over the TCP and UDP video, or you have no previous knowledge of TCP or UDP, definitely check out that video so you can get a brief understanding of how those protocols work, and specifically how we're going to be looking at them here in this scanning and reconnaissance activity that this attacker is doing in this network. So like I said, we're going to be specifically looking at a TCP SynScan, and this type of scan is usually what is done first, and it's also known as a stealth scan or a half open scan because of how it works. So it works by the attacker sending just a TCP SYN packet, and then whatever reply it gets, it never sends back an acknowledgement to the victim. So that's kind of why it's called a half open scan. So this SYN scan is usually used because it's fast, it's reliable, it's accurate, and it's less noisy than the other scanning techniques, which is what gives it its name of the stealth scan. In other lab activities I'll be doing in Wireshark, we'll be looking at other scans that are not TCP scans. So we'll be looking at scans that have fin scan or a bunch of other types of scans an attacker can run on the network during their reconnaissance. So how does the TCP SYN scan work? So essentially, the attacker sends a TCP SYN packet over a range of ports. Most of the time, it's usually between 1 and 1024 because it's faster than going through all of the ports. So it usually go through the standard ports, which we covered in the TCP and UDP video. So check that out. So it sends out a TCP SYN scan, acting like it's trying to establish a channel for communication. So that's like the very first step in the three-way handshake. So we can see that here in the first 13 packets, actually no, the first 10 packets, because right here we have a reply back from the victim to the attacker. So in the first 10 packets, we have SYN packets sent from the attacker to the victim over multiple ports. So we have it's scanning for 443, 143, 3306, 199, and a bunch of other ports. And the source port is an ephemeral port, which was picked at random by the host or the operating system when the attacker was scanning. So we see the attacker is scanning multiple ports here, which is the first stage of the TCP SYN scan. So it sends a SYN packet to the destination, but this is also the first stage of the TCP three-way handshake, right? So that's how the attacker kind of exploits this. This is how the attacker kind of works around the TCP three-way handshake to scan the network, and we'll be looking at how that works. So we start with the SYN scan, right? We start with the TCP SYN packet from the host, from the source to the destination, which in this case is the attacker and the victim. And then, of course, in the three-way handshake, the second thing we're expecting is a reply back from the destination back to the source, and in this case, the victim back to the attacker. So a reply back in a normal TCP three-way handshake will be a SYN ACK, right? Which is the destination responding back to the source that, hey, I received your SYN packet and I'm ready to start communicating, right? So the victim sends back a SYN ACK packet back to the attacker, and we can see a reply back here, somewhere here. We see there's actually a reply back here of the victim sending back a SYN ACK to the attacker, and this is responding at 53. So this is over port 53. So this is the victim is responding back to the attacker over port 53. And the reason why the victim is sending back that SYN ACK packet like it normally should is because the port is open. So the three states a port can usually be in. It could either be in open, closed, or filtered. So when the port is open, the victim will typically respond back to the attacker with the SYN ACK packet as it normally should in a normal TCP three-way handshake. But here's the thing: the attacker never replies back with an ACK packet. Never replies back with an ACK packet. Why? Because that was never its it's his intention. His intention was not to establish communication. It was just scanning to see if the port is open, closed, or filtered. So in this case, with the port being open, the victim replies back with the SYN ACK. So the attacker knows, okay, this port is open, so I can do whatever I want with this port. Now, that's if the port is open. The second scenario or second case could be if the port is closed. And we can see right here, we have a reset ACK packet sent back to the attacker over port 133. And this is usually what happens when a port is closed. So when a port is closed, the victim typically sends a reset packet or a reset ACK packet to the attacker. So the attacker knows, okay, this port is closed. I can't really do anything with that, or I might try to find a way around that. Now, the third and final state that a port could possibly be in is for the ports to be filtered. And in this case, when the port is filtered, there will not be a reply back to the attacker. So the victim would not reply to the attacker. So when it was open, it replied with a SYN ACK. When it was closed, it replied with the RSD or RSD ACK packet. But if it's filtered, it would not reply back to the attacker. So if the attacker does not see any packets back after it sends its original SYN scan, then it knows that that port is filtered. And the reason why a port could possibly be filtered is because of maybe a firewall or a host firewall that's standing in between the attacker and the victim, and is ensuring that the attacker never gets a reply back because it doesn't want the attacker to know what port is open or closed on the victim. So the attacker will never know if the port is either open or closed. The port could be open on the victim, but because of that firewall, whatever intermediary device between the attacker and victim, the attacker would never know if that port is open or closed. So that's kind of how we look at scan activity in network capture. So we can see there's a lot of SYN packets sent over various ports, and we see a couple of replies. We see another reply back to the attacker here for port 25, and then we see more SYN, and all of that. So another way we can look at scans holistically is using the statistics, and going to conversations. We covered how to use statistics in the statistics video, and which is I believe the third video in this series. So if you're not checking it out, please be sure to check it out. So here, if we look at all these different things, we only see two hosts here. So we see one host here and another host, different MAC addresses. And here we see two IP addresses. We don't see any IPv6, and we see a lot of TCP packets, 1,994 to be precise. So if we look at the communication, we see a bunch of packets from the victim right here, which is 64, the 13, the 134, the 52, to the attacker, which is 172, the 16.0.8. But what we're essentially looking for, if we're looking at conversations, is the amount of packets. So if we sort the packets by amount of packets, so we from highest to lowest, we see 5, 2, and 1, and these are the only numbers we see for number of packets here in this view that we have right here. So if we are looking at 5 packets, this essentially shows that a SYN was sent from the attacker and multiple SYN ACK replies were sent by the victim. So when and the attacker sends the original SYN packet to the victim typically responds back with multiple SYN ACK replies because it's TCP. It's trying to ensure that it's connected. It's trying to ensure that there's transmission. So the victim will try as much as possible to respond back with as many SYN ACK replies as possible, waiting for the attacker to respond back because it's expecting a 3-way handshake. But as we already know, the attacker will never respond back. So it starts with one SYN packet from the attacker and then 3 or 4 SYN ACK replies from the victim back to the attacker, showing us 5 packets here. So we see here over port 53. If we looked, we saw some replies from the victim over port 53, and that shows the attacker that this port is open. So we can see here port 53 is open, port 80 is open, port 22 is open, port 133 is open, port 25, port 33. Those are 2. So we see that port 53, port 80, and port 22 are open because we have those 5 packets communicating back and forth between the attacker and victim. And then we have 2 packets. So 2 packets is really, really easy to understand. So it shows that when the original SYN packet was sent from the attacker, there was only one reset packet replied back by the victim. So that shows that the port is closed. We established that when there's a reset packet sent back to the attacker, it shows that the port is closed. So when we see 2 packets, that indicates that the attacker sent the same packet and there was a reset packet sent back and shows that the port is closed. So we can see that port 113 is closed, port 25 is closed, port 31337 is closed, port 113 is closed again, so might have scanned maybe twice or something, and then port 70 is closed. So those 2 packets communicating between the victim and the host explain that these ports highlighted are closed. The rest of it, where we have just 1, shows that there was no reply. So there was only 1 packet sent, which was the original SYN packet from the attacker to the victim. So all of these other ports that we have 1 packet showing for, all these other ports are all filtered by the firewall. So that's a a good way of having that overview or holistic view of some ports in packet capture rather than looking at each packet individually. If you can just come here and just look at the packets, sort by highest to lowest, you'll see the number of packets sent between victim and host, and that way you can discover which ports are open, closed, or filtered by the firewall. We can also look at the ports, so we can see we sort the port by lowest to highest. We can see the attacker essentially scanned for every possible port, so 1, 3, 4, 6, 7, 9, 13, all the way, all the way, all the way, all the way. Scan every single possible port you could ever think of scanning within the amount of ports available. Well, actually, okay, actually got to 36051, which is like half of I believe 6535 ports that exist. So that's a brief overview of how scanning works. And that's all for today's video. Thank you very much for watching. The links to all the mentioned resources are in the description. So the link to Chris Sanders' website and the book I mentioned are going to be in the description. Once again, this is the last video in this series, and I'm super excited for how far this series has come, and I'm looking forward to more series like this where I break down a tool or topic and explain everything I know about it